shall consider few problem on Legendre polynomial. First thing is that the problem is show that integration from 0 to pi Pn of cos theta Pn of cos theta sin theta d theta is equal to 2 upon 2n plus 1 delta mn. Let us substitute x is equal to cos theta. Then dx is equal to minus sin theta d theta. At x is equal to, at theta is equal to 0, x is equal to cos theta is equal to plus 1, and at theta is equal to pi, x is equal to minus 1. So this integration becomes from minus 1 to plus 1 Pnx Pmx dx, which is 2 upon 2n plus 1 delta mn. Now coming to the second one. If the difference between m and n is an integer, is an even quantity, then it is given that m minus n is equal to even. That means both m and n either even or odd. This implies that both m and n are either even or odd. There is no mixing. Then so that 0 to 1 Pnx Pmx dx is equal to 1 upon 2n plus 1 delta mn. Since both m and n are either even or odd, this is even. So we can write this integration 0 to 1 Pn Pm dx is equal to half minus 1 to plus 1 Pn Pm dx, and hence the result follows. Sometimes one encounters an integration which involves the two Legendre polynomial and x is sandwiched between this. How to evaluate this? Remember the recurrence relation of Legendre polynomial was n plus 1 Pn plus 1 of x is equal to 2n plus 1 x Pn of x minus np of n minus 1 of x. We obtain this relation by differentiating the generating function with respect to t. This expression can be written as x Pn of x 1 upon 2 to the power n plus 1, this is 2n plus 1, then n plus 1 Pn plus 1 of x plus np n minus 1 of x. If we substitute this, we get 1 upon 2n plus 1 taken out. Then the integration, this is to use this expression directly, we just interchange between this. So this is Pm of x, then n plus 1 dx. We we write this as integration from -1 to +1. First term, n plus 1 taken out, skipping the arguments, and then for the next term, these are the two terms. Now the first integral on the right contributes when m is equal to this, and this contributes when m is equal to n minus 1. We have used the orthogonality property. The weight normalizing condition is factor is 2 upon 2m plus 1. If we put in the first expression m is equal to n plus 1, so this becomes, there are 2n plus 1 in the numerator, and this factor will be 2n plus 3, plus this is 2n, this factor is there, and this factor is 2n minus 1. Similarly, the integration can be integration of such sort. X square Pn of x can be evaluated likewise, in which case what we need to do is xpm, and we write xpn and use double expansion, so there will be 4 terms involved. Now coming to the Fourier Legendre expansion. Fourier Legendre expansion uses the completeness of the Legendre polynomial as well as the orthogonality property, which enables us to find out the expansion coefficient very easily. Our problem is that we have a function of f of x is equal to x cube minus 7x square plus 4x plus 11. It is defined in the range x plus minus 1, and it's obviously there's an even will be a function. Our aim is to expand it in terms of Legendre polynomial. So you see the highest power of x is 3, so maximum coefficient that will be involved is p3, so we write it as a1 p1 a2 p2 plus a3 p3, no more higher terms, as has been explained. Now coming to the 4x term. 4x is equal to 4 times p1, 7x square. X square, you know that p2 of x is equal to half 3x square minus 1, which gives you x square is equal to 2 by 3 p2 plus 1, so you can write as p2 plus p0. And coming to this x cube term, we know that P3 of x is equal to half 5x cube minus 3x, or x cube can be written as 2 by 5 P3 plus 3x, which can be written as 2 by 5 P3 plus 3P1. So we can replace this and get the expression for in terms of P1, P2, P3. That is, we can evaluate this expansion coefficients. Another problem, which is a bit involved problem, that's why I was a bit reluctant whether this should be worked out or not, and finally decided to work it out. Or show that the problem is so that x to the power m Pn of x dx integrated from -1 to +1 is 0 if m is less than n. This is to show. Recall the Broderick's formula. Broderick's formula for Legendre polynomial is this: Pn of x is equal to 1 upon 2 to the power n factorial dn dx n x square minus 1 to the power n, which we write as 1 upon 2 to the power n factorial n dn x square minus 1 to the power n. Let us consider that this is the integral. So we write 2 to the power n factorial n times I is equal to x to the power m dn x square minus 1 to the power n dx integrated from -1 to +1. The expression, in this expression we have replaced Legendre polynomial by its Broderick's formula. If we integrate it by parts, we consider this is as the first function and this is as the second function. So if we, since integration is the inverse process of differentiation, we can write xm d of n minus 1 operating on x square minus 1 upon n with limits -1 to +1 minus differentiation of this Now you consider this fact. This part has been differentiated n minus 1 times. So still we have a factor x square minus 1, which is 0. So this part is 0. So we are left with minus m If we again differentiate it partially, then we will have minus m, then this part x to the power m minus 1 d to the power n minus 2 x square minus 1 to the power n from -1 to +1, and this differentiation gives you m minus 1 d of n minus 2 x square minus 1 to the power n dx minus 1 to +1. This part is 0, so the result is m into m minus 1 integration from -1 to +1 I have missed the factor x to the power m minus 2. Yes, and this process can be continued m times, so k times, so we get you see that if k is equal to m, this is a constant, and for k greater than m, this is 0, this integrand is 0, and this part, coming to this part, what happens to if k is equal to m, x to the power m minus k is x to the power 0 is equal to 1. Any further differentiation will lead to the 0 value. And what happens to n minus k part? N minus k part is simply n minus m. Since m is less than n, since this is a positive quantity, so still the differentiation exists and this part gives you 0, so the result is 0 if m less than n. So we have come to the end of the Legendre differential equation. Let me just summarize what I have done. We have started with the differential equation 1 minus x square y double prime minus twice we have started with this differential equation 1 minus x square y double prime minus twice x y prime plus alpha y is equal to 0, where alpha is any real quantity. Our region of we are interested for the solution in the range x less than equal to this, because this lies within two removable singular point. This differential equation has two removable singular points, at one at x is equal to plus 1, other one is at minus 1. So we are interested between this solution in this range and which fits physically with the spherical polar coordinate, that is x is equal to plus 1 is the positive z axis and x is equal to minus 1 is the negative z axis. And we see that for any real value of alpha, both the solution are divergent on the z axis. So to get rid of this, we use special value of alpha as L into L plus 1. And for even value of L, the even series is a polynomial, while the odd series is an infinite series which has divergence. And for odd value of alpha L, the odd polynomial becomes the odd series solution becomes a polynomial. The polynomial solution of Legendre differential equation is called Legendre Polynomial and is denoted by this, and the infinite series solution is denoted by QL of x. So the general solution of the Legendre differential equation for Legendre differential equation, where this is can be written as AL PL of x plus BL QL of x. When the z-axis is included in the system, we put BL is equal to 0. If z-axis is not included, then there is non-zero value of BL. Then we have obtained this. We have seen that the PL is a polynomial of order L. PL is a polynomial of order L, and it is an even polynomial for even values of L, and it is an odd polynomial for odd values of L. We then come to the Rodrigues formula, which gives you PL of x is equal to 1 upon 2 to the power L. This is a known function, and if we differentiate it successively, we get different values of pi. There is another way of getting the Legendre polynomial. This is the generating function, which is very helpful in getting the Legendre polynomial or the other special functions of higher order. This can be written as t to the power L PL of x, and this formula can directly be applied to the multiple expansion of 1 by r potential. Then we have by differentiating this partially with respect to t, we get a relation between the Legendre polynomial of different orders, which is known as the recursive relation, and differentiating it partially with respect to x, we get an expression for the derivative of the Legendre polynomial. These two are the basic recurrence relation which can be manipulated suitably to get other relations. The book by Biswas has nicely compiled all such recurrence relation of Legendre polynomial. Then coming to the orthogonality property, we see that the Legendre polynomial in the range -1 to +1 forms an orthogonal set of basis function. This is the result is orthonormality relation is this. And furthermore, the Legendre polynomial forms a complete set in the interval ±1. So we can expand a function in the region ±1 as AL PL of x L is equal to 0 to infinity. The orthogonality relation readily allows us to find out AL as AL is equal to 12 plus 1 by 2 f of x PL of x dx from -1 to +1. This is the whole summary of what we have done in Legendre polynomial. In few books, it is found that the solution of Legendre polynomial has been sought using Frobenius method. Let me spend a bit on it. As x is equal to 0, as x is equal to 0 is a regular point, of Legendre differential equation, we assume the solution in this form, the power series method, with C0 not equal to 0. Somebody uses the solution as like this: ck x to the power m plus k with C0 not equal to 0. Then we need to know the index. The initial equation is obtained as 0 and 1. We know that when the roots of the initial equation differs by an integer, the higher root will definitely provide a solution. We find that this higher root provides the solution that we have obtained earlier. And if we put m is equal to 1, it just reproduces a part of the solution. So this does not give you any linear independent solution. It just reproduces a part which is obtained if m is equal to 1. So by this we complete our discussion on Legendre differential equation. Next we shall take up harmonic differential equation.